Okay, thank you all for coming back in, having a nice break. I think we already saw some good discussions happening here. I'm happy to turn this over to Gail Schaefer, the director of the SHAR Array, and she's going to talk about the science being done with optical interferometers, which is very exciting. Gail?
It's great to be here. So I'm coming down from Mount Wilson, which you can see just over there up by the radio antennas on the mountain. So that's where this photo up here was taken. So I'll be giving, have the opportunity to share with you a whole bunch of exciting science results that are coming out of long baseline optical and infrared interferometers. So I figured I would start just by giving a brief overview of the arrays that had collected most of the data that I'll be showing. So these include the SHAR array up at Mount Wilson, which combines the light from 6 1-meter telescopes with baselines up to 330 meters. There's the Very Large Telescope interferometer run by ESO in Paranal, Chile, and that you can either combine the 4-unit telescopes, the 8 meters, or there's also smaller 1.8-meter telescopes that you could use also. There's the Navy Precision Optical Interferometer in Anderson Mesa in Arizona. The Large Binocular Telescope Interferometer at Mount Graham in Arizona. And also up and coming is the Magdalena Ridge Optical Interferometer. And Michelle this morning shared some planning for that. So that's under construction right now. And so the basic measurement of a stellar interferometer is basically to measure the sizes of stars. And so this is an empirical Hertzsprung-Russell diagram plotted on there. There's nearly 700 stars that have had their angular diameters measured with interferometry. And so if you get the angular diameter and you combine it with a distance estimate to the star from, say, Gaia parallaxes, you get a direct linear radius for the star. And if you combine that diameter with the total flux coming from the star, it's a way to get an empirical effective temperature. So in this HR diagram over here, it's plotting the temperature versus the luminosity. And basically with interferometry, you can measure stars all along the, and the plotting symbols here are basically the size corresponds to the logarithm of the radius of the star. So you actually get like a representation of how large these stars are. So within long baseline interferometry, you can measure stars all along the main sequence from hot, massive O and B type stars down to cool, low mass M type stars. And you can also look at stars, how they evolve off the main sequence into the giant and supergiant branches. So you can look at how stars evolve over time. And you can use these radius and effective temperature measurements then to compare with evolutionary models as a way to estimate masses and ages of stars. And you can also use those fundamental parameters to also test models of evolution for different stages of star formation. And you can also use these fundamental parameters to also determine scaling relations and surface brightness color relations. So when you have a star that is too far away to resolve spatially, you can get information about how big the star is based on its brightness and the color of the star. And so one important type of stars that you can measure diameters of is exoplanet host stars. And so again, by knowing the radius and effective temperature of the host star, you can get a mass and age of the star from the evolutionary tracks. And all those properties of the star allow you to determine, revise estimates on the habitable zone around stars of where, whether a planet that you find might be in an area where life is possible. And also, if this star is a transiting exoplanet, you can get estimates of the radius of the planet itself based on the timing of this light curve. But those inferred diameters of the exoplanet depend very strongly on what your actual size of the star is. So the interferometric sizes then allow you to get masses and radii of the planet themselves based on the stellar properties. You can also look at stars that are pulsating. So this is a Cepheid variable star. And they're important because they're a fundamental rung in the cosmic distance ladder. And so you can, by combining variations in the radial velocity of the star, so that kind of puts on a physical size of the variations with the angular diameter variations, you can get a pulsational parallax out of the star and used to calibrate distance scale measurements. And if your star is big enough, not only can you do basic size measurements, you can also start doing image reconstructions of what surfaces of other stars actually look like. So on the left of this diagram here, we have images of some rapidly rotating stars. So when a star rotates quickly, it becomes bulged at the equator and flattened at the poles. And so with the interferometry, you can measure that oblateness of the star itself. And there's two other effects you can see in these images. One is around the limb of the star. The brightness drops off, so you can start to characterize empirically what limb darkening looks like on the star. And there's one other effect here, and that since these are rapidly rotating stars, the equator is bulged and further away from the core of the star than the poles are. So the bulged equator is going to actually appear cooler than the poles. So that's an effect called gravity darkening. You can also look at magnetically active stars that have star spots on their surface. This little movie here is of Zeta Andromeda, and you can see over this full month-long rotation cycle, you can see the star spots rotate through your field of view. And these diagrams down here are just the whole surface unraveled, so you can see all the where the spots are in both latitude and longitude. Another spotted star, Lambda Andromeda. And then also for giant stars and supergiant stars, you can start looking at convection patterns on the surfaces of these stars. And you can look to see the size of the convection cells and also how they change over time. And at the end of stars' lives, they tend to lose mass in the end stages. This is a hypergiant star, RW Cephei, that recently went through this great dimming event, kind of similar to what Betelgeuse went through several years ago. Then the magnitude dropped down, the brightness dropped down, and then re-brightened. And by imaging the star in the, at the minimum and on the rise up, you can generate an image of what the star looks like. And it turns out that part of the stellar surface here was blocked. So the idea here is that the star likely had a large ejection of material out. And as the material went away, it cooled and formed dust. And if you're aligned at the right angle, that dust cloud will block out part of the stellar surface. And so that's kind of what you're seeing going on in these images here. And also at the end stages, if you can catch a nova explosion, you can actually see how novae change over time. So this is a nova that went off in 2013 in the constellation of Delphini. And it was basically discovered by an amateur astronomer in Japan and imaged up at Chara. And you can see the angular size of the nova increase basically over a little over a month versus of time. And in the early days, we actually got image reconstructions of what that nova looks like. So based on how the angular size changed over time, you can kind of put generate a model of how the opaque inner core is very bright, and then as the material cools off, it becomes more transparent. And so the changes in the contributions from these two components kind of can explain some nonlinearity in this expansion curve down here. And at later times, you see a big jump in the angular size that coincides with, in the light curves, the visual band brightness kind of decayed over time, whereas the near-infrared brightness kind of boosted up a little at the end. So this could imply that in the later stages, dust might have formed in the outer layers, which could contribute to the increase in the near-infrared emission and also an increase in the apparent angular size at large radii. Interferometry is very good at detecting close companions to stars. And one of the fundamental things you could do with binary stars is measure stellar masses. So this is just basically a multiple star in the constellation of Orion. There's many components, but this A component that's buried in here is actually a spectroscopic binary. And so using interferometry, you can map the orbit over time. And basically, by knowing how far apart the stars are apart and how long it takes to rotate, to orbit, you can get the masses and distance with very high precision, down to like 1% to 3% precision. This is a recent result that came out on Polaris, which is actually the nearest and brightest Cepheid variable star and our North Star. Polaris it's actually in a triple system. It has a very wide companion, Polaris A and Polaris B. But Polaris A itself is a close companion. This is an image with the Hubble Space Telescope, and you can see a very faint companion AB there, which was known spectroscopically and detected for the first time with Hubble. It has an eccentric orbit, so at closest approach, it becomes basically the companion gets hidden in the light of the Cepheid during closest approach. So you need basically interferometry to be able to resolve the faint companion at even closer distances. So using CHARA, we got the companion as it was going through closest approach. But as we were looking at the data, we realized there was more asymmetries on the surface of the star than could be explained by the companion itself. And it turns out there's spots on the surface. So these could be, and they change over time, so they could be either related to rotating spots on the surface. It could be related to the pulsation cycle, or maybe even convection cells. So monitoring this over time could give you some clues about what's actually going on the North Star that we know so well. And even closer in binaries, you can look at binaries that are exchanging mass from one companion to the other. And not only can you map the orbit over time, but you can start seeing tidal distortions in the mass donor star and like a elongated thick accretion disk around the mass gainer. And you can also, with the interferometry, you can get very high astrometric precision. Both VLTI and CHARA can get down to tens of microarcseconds in precision. And so this is just a wide binary orbit. But if you look up at the top here and zoom in, you notice that it's not just regular orbital motion in there. There's these little loops here. And basically, this is the effect of a third unseen companion in there that's wobbling the primary star. So basically, at this sensitivity, you can get down into maybe the brown dwarf, hot Jupiter range of planet detection in known binary systems. And one last thing for the binary star section here is you can also do eclipsing binaries, where you have the light from the two stars are arranged inclined along your line of sight, so that you can see when one star passes in front of the other, you see a dip in the brightness. And this is Epsilon Rigel that has a very flat and long eclipse, and it was kind of hypothesized that the companion that's orbiting around is hitting in this thick disk of material. And so when you actually image that with interferometry, you can actually see when the eclipse starts, this bottom part of the star being blocked out by this accretion disk, this thick disk that's hiding the companion nearby. And this kind of gives you the structure of that disk going through. And you can also do disks directly. This one here was like kind of a disk in silhouette that you can map out. But you can also do disks directly around, planet-forming disks around young stars. Using radio interferometry, you can get the cool disk, the cool dust in the outer regions of the disk. Using optical and near-infrared interferometry, you can peer into the inner warm regions of the disk where planet formation is likely to occur. And so these are some images of disks around young stars, both with CHARA and VLTI. And you can actually start to see some clumpy structure in these inner disks and brightness distributions that change over time. And you can also look for, this is a little result from the LBTI on nulling interferometry that you heard about before. So this is basically blocking out the light of the star and just seeing how much emission is around that star. So looking for exozydal dust. And this has impact on planet detection around other stars, whether you can actually detect and measure Earth-sized planets. If the exozydal light is too much, you won't be able to pull out the planet from that signature. So LBTI basically had a survey where they looked at 38 stars and just nulled out the central star and measured the excess light that's left over from this exozydal dust. And so they basically found a correlation between the presence of cold dust far out and the presence of warm inner dusk in these mid-infrared wavelengths. And they also found that sun-like stars have relatively low exozydal dust in the habitable zones. So maybe this is good news for potential planet finding of terrestrial planets around sun-like stars. And then, so all these results that I just showed previously were all results that you're finding fringes on the star that you're looking at. And I include this diagram here briefly, but this is, Michelle mentioned this morning, is the dual field mode, where you can boost your sensitivity. If you have a bright nearby star, you basically have two independent combiners that are one's looking on the bright star, and then you can offset the second combiner to your faint star. And so this is a mode that's enabled at the Very Large Telescope Interferometer with the gravity beam combiner. And basically, you can get down to almost 20th magnitude, going from basically taking your reach 10 magnitudes fainter by using this phase referencing mode. And so these are some results from that VLTI phase referencing mode. So one thing that you do is you can look at these directly imaged planets around stars. So this image here is a Keck image of HR 8799. You can see the little directly imaged planets going around. And with VLTI gravity, you can actually phase lock on the bright central star and then offset your second combiner to get fringes on your second star. And so this allows you to get a very precise astrometric measurement of your planet going around, so it impacts on your orbit fitting for the planet. But you can also isolate the light from the exoplanet. And so if you then disperse your light in your beam combiner, you can actually get spectrum directly of your planet. So there's been a few systems like this that have been done. One of the main motivations of building gravity was to look at the galactic center. So these are stars orbiting the supermassive black hole in our Milky Way galaxy. And this is let me go one more. Yeah, this is the orbit of this one star coming in. And basically gravity observed it during closest approach down here, and allows you to really test general relativity in this high mass supermassive black hole region. And this is just basically a three epochs in March, May, and July of 2021. And you can see basically the three epochs where these stellar orbits lie. And this might be out of battery. Oh wait, no, there we go. And basically the orbits of those three stars around the central supermassive black hole. You can also look at supermassive black holes in other galaxies. So this is really another region where VLTI is a forte on, because you can get that high sensitivity if you have a bright phase reference source. And so this is actually a mid-IR image of the active galactic nuclei in NGC 1068. And so basically this is looking at the paradigm of the structure of the dust torus around that supermassive black hole in the galaxy. And basically, active galactic nuclei come in two types, and the standard matter predicts that differences in what you see in these active galactic nuclei will depend on your viewing angle, basically. And so on the left here, in NGC 1068, you basically have your edge-on disk, and this is actually the VLTI image of the, basically your opening angle of the disk here. This bottom image kind of shows you what part of the AGN you're looking at. And up at Chara, we pushed limits and actually did our first AGN observation of NGC 4151. And this is a face-on image, so you can basically peer directly in that big dusty torus, more at the inner regions of the dust sublimation region. Okay, and then I thought I would take a minute to basically take a look at past and future priorities for optical long baseline interferometry in past astronomy decadal surveys. So every 10 years, the astronomy community comes together to define priorities, both for federal funding agencies and Congress, of where priorities lie. So this is kind of a fun exercise, and I went back and started in the 1990s, which was basically my introduction to astronomy, professional astronomy here, and went back to the decadal surveys. And back in the 1990s, for ground-based priorities, in terms of moderately sized programs, the two main priorities were adaptive optics and interferometry. And interestingly, in that decadal report, there was a whole section on the moon as an observatory site, mentioning high sensitivity from having no atmosphere up there. And this little diagram here was actually an artist's conception in the decadal report of a lunar interferometer back in the 1990s, in which they were kind of it wasn't like you need to fund this, but it was just generating ideas of what you could do. And they actually mentioned like maybe kilometer-sized baselines, and the advantages of you don't have the Earth's atmosphere to deal with, and no spacecraft positioning for being free-floating spacecraft. But also in the 1990 and also the 2000 decadal surveys, there was a big emphasis on space-based interferometry. This is with the Space Interferometry mission, which later became SIM-LIGHT. But this was an astrometric mission that was basically looking for the wobbles of planets around other stars. So just looking astrometry of a large sample of stars. That was followed on by the terrestrial planet finder, which was the goal there was to basically do nulling and characterize Earth-like planets around other stars. So back in like the 1990s and 2000, this was like a big emphasis to put an interferometer in space. And then that suddenly all came to an end in a footnote in the 2010 decadal survey, where basically the survey said, in considering possible exoplanet missions for the next decade, the committee gave serious consideration to SIM-LIGHT, but decided against recommending it. And basically, space-based interferometry kind of fell out of the interest of NASA at that point. And the reasons they gave was the large cost, the long time for launching, and also this, in the meantime, the success of the Kepler mission for detecting thousands of exoplanets using transit technique, which is a lot faster, efficient, and cheaper than the space interferometry mission was going to be. That brings us to our most recent decadal survey, which there was more of a strong emphasis on ground-based interferometers. And there was a suggestion of a concept of a mid-infrared interferometry for searching for life on exoplanets. Also in the panel from stars, the sun, and stellar populations, they recommended continued funding for all 3 US-based interferometers, Char-Array, Navy Precision Optical Interferometer, and Magdalena Ridge Optical Interferometer. And for future needs, they specified, like, it would be nice to go out to 1 kilometer baselines, larger apertures, and broad wavelength regions. And to basically do full characterization of all stars, and also getting into down to brown dwarf radii. And yeah, so brings us to today. So in this survey, there was basically not really much of a mention of either space-based or interferometry from the moon. Which brings us to our workshop today, I guess, or this week, of looking for opportunities to do milli to microarcsecond spatial resolution. So the main advantages here are high sensitivity and stability for the being on using the moon as your base for the interferometer. And resolution, you can potentially think of, going to longer baselines, but also without having an atmosphere in between to deal with. You can also think about improving resolution by going to shorter wavelengths. So shorter wavelengths optical, UV, and some of the science drivers, which I'm looking forward to maybe bringing these more fully complete during this week, of radii of the coolest stars and brown dwarfs, close companions around planet-hosting stars. So these are, if you have an exoplanet around the star, if that star is actually a close binary, it's going to dilute the transit measurement. So basically, it's going to impact what you think the properties of the planet are going to be. You can look at the radii and inner regions of young stellar objects. If you have high enough resolution and sensitivity, you can start looking at sizes of young stars, so stars that are still contracting to the main sequence phase. And of course, going to fainter targets, you get more and more of these active galactic nuclei that fall into sensitivity range. And these are just kind of food for thought for the week, and I'll end there.